This tutorial corresponds to Roman numeral 2 in the Honors Gas Laws Notes packet. Gases are really important in a lot of things. To understand the gas laws means that we understand tire pressure, why soda can stay carbonated or lose its carbonation and become flat, as well as why things tend to float like balloons in the air. The first law that we're going to look at is called Boyles' law. By definition, at constant temperature, the pressure and volume of a sample of gas are inversely proportional. What that means is, as one value goes up, the other value is going to go down. Here we see that there's some gas particles, these black little dots are gas particles, in a certain container. Remember that gas pressure is caused by the collision of gas particles. Well, this is pressed down into a smaller volume. Notice over here in this V2 smaller volume, the second volume, the particles are closer together. Well, obviously if the particles are closer together, they're going to bump into each other more often. Therefore, the pressure is going to be increased. So if I decrease volume, I increase the pressure. Likewise, if the volume is increased, there's going to be less pressure. Again, that's called an inversely proportional relationship. And we can do what's called a proportional equation. P equals K over V. P is for pressure, V is for volume. That K there is a constant. And what that means is that depending on what kind of system we're working with, there's going to be a constant of pressure being inversely proportional to volume. The actual equation that we can use to calculate problems is P1 times V1 equals P2 times V2, where P1 and V1 are the initial pressure and volume, P2 and V2 are the final pressure and volume. There is a graph curve that goes along with any inversely proportional relationship. It looks like this, where it just kind of does a little loop there. If you see pressure on the x-axis, volume on the y-axis, what you're going to see is that as the volume decreases going down, the pressure is going to increase going across. Inversely proportional. Let's try a mathematical example. A balloon is filled with 32 liters of helium gas at 1.0 atmospheres. What is the volume when the balloon rises to an altitude where the pressure is only 0.25 atmospheres? As we've done in previous types of problems, let's identify our variables. We're looking for a P1, V1, P2, and V2. I'm going to go through and I highlighted 32 liters, 1.0 atmospheres. It asks what is the volume and 0.25 atmospheres. Those are the different components that will be involved in the equation. The 32 liters is a volume. Since it's the first volume, I'm going to call it V1. 1.0 atmospheres is a pressure. Since it's the first pressure, I'm going to call it P1. I'm looking for V2, and I have a second pressure, which I'll call P2. Now that I've identified the parts, I'm going to go ahead and plug them into the equation. 1.0 atmospheres times 32 liters equals P2, 0.25 atmospheres, times V2, my unknown. Excuse me. So if I multiply on the left side, I have 32. On the right side, I have 0.25 times V2. To solve, I'm going to go ahead and do 32 divided by 0.25. The reason I'm going to divide by 0.25 is because it's now being multiplied by V2. Whenever I want to isolate a variable, in this case I want to isolate V2, I'm going to do the opposite of what's being done. So whereas it's being multiplied by 0.25, instead I'm going to divide by 0.25. 32 divided by 0.25 is 128. Of course, I want to pay attention to significant figures. I look at all of my givens or knowns. Each of them has 2 sig figs, so I'll go with 2 sig figs in my answer. That's 130 liters. Make sure that you check the math and know how to do it for yourself. The second law that we're going to discuss today is Charles' Law. By definition, at a constant pressure, the volume of a gas is directly proportional to its Kelvin temperature, i.e. if one increases, the other increases. Notice that I highlighted Kelvin because it has to be in Kelvin. Remember that the Kelvin scale has no negative numbers. Here's an example of Charles' Law. So this balloon is in cold water. Have you ever noticed that if you leave a balloon out on a cold day, it'll tend to shrivel up a bit? Once it got into this warm water, look how much larger it grew. So what happens is the particles have a higher kinetic energy. And as they have a higher kinetic energy, they expand or they spread out, making a higher volume. Maybe you've noticed with your tires on your car that when it's colder outside, they tend to lose a little bit of air. But if it's a really hot day, they might gain some air. Usually it's a minimum amount and we don't have to worry too much about it. But if you have a leak or some kind of an issue with your tire where maybe you've got a little too much air in it, a cold or warm day might make enough impact. So again, that is a directly proportional relationship. If temperature goes up, volume is going to go up too, and vice versa. The proportional equation, V volume is equal to K a constant times T temperature. Our actual equation, we're dividing this time. V1 over T1 equals V2 over T2. Please note that these slashes are division, so it's V1 divided by T1 equals V2 divided by T2. Just like inversely proportional relationships, directly proportional relationships have a graph. It is a straight line going upward, volumes going up, temperatures going up at the same time. So this is a graph for directly proportional relationships. Let's look at the example. Go ahead and pause right now. Just like we did with that other problem, try to identify each part of the equation. Look for your V1, T1, V2, T2. Hopefully you found T1 is 27 degrees Celsius, but as you know, we have to use Kelvin. So when I plugged into the equation over here, I used 300. V1 is 4.0. V2 is what we're finding. And T2, again, has to be in Kelvin. So I added 273 to the 57 to get 330. When you solve one of these problems, you probably want to use cross multiplication. It's up to you exactly how you want to solve, but usually I found that students like to use cross multiplication. What that means is I take the top number from this side times the bottom number from this side, and that's going to be equal to the top on this side times the bottom on this side. So in other words, 4.0 times 330 equals V2 times 300. On this side, 4.0 times 330 equals 1320. I have V2 times 300. Now think about how I can isolate the V2. Right now I'm multiplying by 300. The opposite would be to divide both sides by 300. So I ended up dividing 1320 by 300, and I get 4.4 liters. This is the proper number of significant figures. If I look at all of my knowns, they all have 2 significant figures. Now, as you move on to your homework, please beware of units. First off, we've already said, temperature must always be in Kelvin. Any unit may be used for volume or pressure, but make sure that both sides match. For example, on your homework, The first problem has two pressures. One of the pressures is in atmospheres. The other pressure is in millimeters of mercury. It doesn't matter which one you use, but you either have to change the atmospheres to millimeters of mercury, which I would say might be the easier way, or you could change millimeters of mercury to atmospheres. If you do, just make sure that you give yourself enough numbers to pay attention to sig figs. Another thing I want you to make sure to pay attention to, you might have extra information in the problem. Look for keywords like pressure is constant or it's the same temperature. That'll tell you which one to use, Boyle's Law or Charles' Law. Good luck with the problems, and we'll go over them tomorrow in class together.